In physics or engineering education, a Fermi problem, Fermi quiz, Fermi question, Fermi estimate, or order estimation is an estimation problem designed to teach dimensional analysis, approximation, and such a problem is usually a back-of-the-envelope calculation. The estimation technique is named after physicist Enrico Fermi, as he was known for his ability to make good approximate calculations with little or no actual data. Fermi problems typically involve making justified guesses about quantities and their variance or lower and upper bounds. Historical background: an example is Enrico Fermi's estimate of the strength of the atomic bomb that detonated at the Trinity test, based on the distance traveled by pieces of paper he dropped from his hand during the blast. Fermi's estimate of 10 kilotons of TNT was remarkably close to the now accepted value of around 20 kilotons. Examples: the classic Fermi problem, generally attributed to Fermi, is, how many piano tuners are there in Chicago? A typical solution to this problem involves multiplying a series of estimates that yield the correct answer if the estimates are correct. For example, we might make the following assumptions: there are approximately 9 million people living in Chicago. On average, there are 2 persons in each household in Chicago. Roughly 1 household in 20 has a piano that is tuned regularly. Pianos that are tuned regularly are tuned on average about once per year. It takes a piano tuner about 2 hours to tune a piano, including travel time. Each piano tuner works 8 hours in a day, 5 days in a week, and 50 weeks in a year. From these assumptions, we can compute that the number of piano tunings in a single year in Chicago is 9 million persons in Chicago, /A equals 225,000 piano tunings per year in Chicago. We can similarly calculate that the average piano tuner performs 50 weeks year, 5 days week, 8 hours, 2 hours to tune a piano, equals 1,000 piano tunings per year per piano tuner. Dividing gives 225,000 piano tunings per year in Chicago, equals 225 piano tuners in Chicago. The actual number of piano tuners in Chicago is about 290. A famous example of a Fermi problem-like estimate is the Drake equation, which seeks to estimate the number of intelligent civilizations in the galaxy. The basic question of why, if there were a significant number of such civilizations, ours has never encountered any others, is called the Fermi paradox. Advantages and scope: scientists often look for Fermi estimates of the answer to a problem before turning to more sophisticated methods to calculate a precise answer. This provides a useful check on the results. While the estimate is almost certainly incorrect, it is also a simple calculation that allows for easy error checking, and to find faulty assumptions if the figure produced is far beyond what we might reasonably expect. By contrast, precise calculations can be extremely complex, but with the expectation that the answer they produce is correct. The far larger number of factors and operations involved can obscure a very significant error either in mathematical process or in the assumptions the equation is based on, but the result may still be assumed to be right because it has been derived from a precise formula that is expected to yield good results. Without a reasonable frame of reference to work from, it is seldom clear if a result is acceptably precise or is many degrees of magnitude too big or too small. The Fermi estimation gives a quick, simple way to obtain this frame of reference for what might reasonably be expected to be the answer, giving context to the results. As long as the initial assumptions in the estimate are reasonable quantities, the result obtained will give an answer within the same scale as the correct result, and if not, gives a base for understanding why this is the case. For example, if the estimate tells you there should be 100 or so tuners but the precise answer tells you there are many thousands, then you know you need to find out why there is this divergence from the expected result. First looking for errors, then for factors the estimation didn't take account of. Does Chicago have a number of music schools or other places with a disproportionately high ratio of pianos to people? Whether close or very far from the observed results, the context the estimation provides gives useful information both about the process of calculation and the assumptions that have been used to look at problems. Fermi estimates are also useful in approaching problems where the optimal choice of calculation method depends on the expected size of the answer. For instance, A Fermi estimate might indicate whether the internal stresses of a structure are low enough that it can be accurately described by linear elasticity, or if the estimate already bears significant relationship in scale relative to some other value, for example, if a structure will be over-engineered to withstand loads several times greater than the estimate. Although Fermi calculations are often not accurate, as there may be many problems with their assumptions, this sort of analysis does tell us what to look for to get a better answer. For the above example, we might try to find a better estimate of the number of pianos tuned by a piano tuner in a typical day, or look up an accurate number for the population of Chicago. It also gives us a rough estimate that may be good enough for some purposes, if we want to start a store in Chicago that sells piano tuning equipment, and we calculate that we need 10,000 potential customers to stay in business. We can reasonably assume that the above estimate is far enough below 10,000 that we should consider a different business plan. Explanation: Fermi estimates generally work because the estimations of the individual terms are often close to correct, and overestimates and underestimates help cancel each other out. That is, if there is no consistent bias, a Fermi calculation that involves the multiplication of several estimated factors will probably be more accurate than might be first supposed. In detail, multiplying estimates corresponds to adding their logarithms. Thus one obtains a sort of Wiener process or random walk on the logarithmic scale, which diffuses as. In discrete terms, the number of overestimates minus underestimates will have a binomial distribution. In continuous terms, if one makes a Fermi estimate of n steps, with standard deviation units on the log scale from the actual value, then the overall estimate will have standard deviation, since the standard deviation of a sum scales as in the number of summands. For instance, if one makes a 9-step Fermi estimate, at each step overestimating or underestimating the correct number by a factor of 2, then after 9 steps the standard error will have grown by a logarithmic factor of so. Thus one will expect to be within 1/8 to 8 times the correct value within an order of magnitude, and much less than the worst case of erring by a factor of. If one has a shorter chain or estimates more accurately, the overall estimate will be correspondingly better. See also, dead reckoning, hand waving, heuristic, orders of approximation, Stein's example. Notes and references. Further reading. There are a number of university-level courses devoted to estimation and the solution of Fermi problems. The materials for these courses are a good source for additional Fermi problem examples and material about solution strategies. 6.055J/2.038J The Art of Approximation in Science and Engineering taught by Sanjoy Mahajan at the Massachusetts Institute of Technology. Physics on the Back of an Envelope taught by Lawrence Weinstein at Old Dominion University. Order of Magnitude Physics taught by Stolfini and Peter Goldrick at the California Institute of Technology. Chapter 2, Discoveries on the Back of an Envelope from Frontiers of Science, Scientific Habits of Mind taught by David Helfand at Columbia University. External links. The University of Maryland Physics Education Group maintains a collection of Fermi problems. An example of a Fermi problem relating to total gasoline consumed by cars since the invention of cars and compares it to the output of the energy released by the sun. Lawrence Weinstein and John A. Adam, Guesstimation, Solving the World's Problems on the Back of a Cocktail Napkin Princeton University Press. 2008. ISBN 0-691-12949-5. ISBN 978-1-4008-2444-1. A textbook on Fermi problems. Aaron Santos, How Many Licks? Or, How to Estimate Damn Near Anything. Running Press. 2009. ISBN 0-7624-3560-7. ISBN 978-0-7624-3560-9. How should mathematics be taught to non-mathematicians? Timothy Gowers.